So we have found the number of atoms on the surfaces, right? Now it's saying we should find the obtain the number of atoms on the top and bottom surface. So it's like it's calculate, obtain, calculate. It's basically the same thing, just using a different like grammar or something. So we know that at the surface here, under normal circumstances, atoms will be here, right? Atoms are spherical, so they are going to be something like this. Like this. This is what we have to expect since they are spherical. But then if we try and consider them this way, our calculation will be difficult here at the surface. So we are going to slice through like this at the surface here so that we can get it to be plane. Okay, and now so if we are slicing that to be plane so that we can calculate the area of this surface here, and then if we find the area of one atom, so first of all we calculate the area of this surface. We've sliced it, so we have like we now have a surface like this. Instead of having a surface with atoms like bumpy like this, you see, calculating the area of such a surface would be difficult because you have all these atoms here and they are not uniform. So you are going to have a sloping like this. But then if we slice through, we are going to have a perfect surface that we calculate what we want to find. So when we do that, we find the area of the surface of this. Then we find the area of one atom. Then we divide the area of the surface by the area of one atom. Then we find the total number of atoms here. So that's what we are going to do. We have found the radius of this surface. You know, area is, so this is step 5. Area is pi r squared, right? And we need the radius of that surface. The radius of that surface, we found it to be here. The radius of the inner circle. The radius of the inner circle, we found it to be 9.6806 nanometers. So we can simply find the area. That will be pi, which is 3.142, as we are using it in our calculations, times 9.6806 squared. So 3.142 times 9.6806 squared. And we have the area of the inner circle to be 294.44, let's say 94 nanometers squared. So its area is squared because it's area we are working in now. Now we have to find the area of one atom. So area per atom, or the area of one atom. That's also pi r squared, right? So we've sectioned through the atom and we have like, now we have a flat thing. Atoms will be spherical, but because we are cutting through, we have a flat surface now, so we can now find the area of like what we have here. So we have the radius of the atom to be 0.1597. We calculated that here. The radius of the atom to be the radius of a silver atom is 0.1597. So we go on, we have pi, which is 3.142 times 0.1597 all squared. We do that. Okay. And we have the area of one silver atom to be 0.080134. Let's say 34. Okay, so this one, like, write it to your convenience, but don't just write like 3 decimal places because there's a 0 here. If you reduce the decimals here, it can affect your answer. That's why I wrote it quite fine. You can even write it 3385. Okay, let's keep it at 3385. It depends on you. The more your decimals, the more accurate your value will be. So now we have the area of this part, and we have the area of one atom occupying here. So if we divide the total area by the area of one atom, we can find the total number of areas, the total number of atoms there. Alright, so let's go. The number of atoms on the top surface, is this divided by this. So 294.4494 nanometers squared over 0.0801338 nanometers. This nanometers squared. So nanometers squared. You can say per atom because it's the area of one atom, so per atom. So let's do the calculation. 294.4494 over 0.08013385. We're going to have 3674.4697 atoms. So this is the number of atoms on the top surface. Okay, on the top surface. Now, in the beginning, we said that we are considering with my pen, we are considering the number of atoms here to be equal to the number of atoms here. Okay, because there's a pen, that's why here is pointed. But then for a cylinder, here will be the same as here. Like they are identical. Okay, they are the same. So the number of atoms on the bottom surface will also be 3674.4697 atoms, right? So if we want to find the number of atoms on the top and bottom, we just multiply the number of atoms on the top by 2. So 2 times 3674.4697 2 times 3674.4697, that will give us 7348.9394 atoms. So this is the number of atoms on both top and down, okay, or top and bottom, however you want to call it. So there's it, right? Okay. Now we've done this. So 6, it said calculate the total number of atoms on the surface. So the total number of atoms on the surface is the number of atoms on the curved surface plus the number of atoms on the top surface plus the number of atoms on the bottom surface. That's what we are going to do. We found the curved surface already. We found the top and bottom, and we know the top and bottom is twice the top or twice the bottom, any of them. Okay, so we just add the number of atoms on the curved surface here to the number of atoms on the top and bottom here. Then we get the total number of atoms on the surface. So let's do that. So I think that's 6. The total number of atoms on the surface will be 115. Now let me write it out first. Will be the number of atoms on the curved surface plus the number of atoms on the top and down, or top and bottom. So that's 115. Have 115,649.1392 649.1392 plus number of atoms on the top and bottom. That's what we have here. 7348.9394. So we do the calculation. 115,649.1392 plus 7348.9394, and we obtain 122,998.0786 atoms. Okay, so the number of atoms on the surface is 122,998.0786 atoms. Alright, so we've done this. Now 7 said obtain the number of atoms in the entire volume of the cylinder. Okay, so 7. We are come to find the number of atoms in the entire volume of the cylinder. We know that we have the volume of the cylinder and we have the volume of one atom. So if we want to find the number of atoms in the whole cylinder, we divide the volume of the cylinder by the volume of one atom. Okay, it's like you have a box full of oranges. You know the volume of the whole box, okay, and you know the volume of one orange. If you want to find the number of oranges in that box, simply divide the total volume of the box, which you know, by the volume of one orange, and you find the number of atoms, the number of oranges you have in that box. So that's like the concept we are employing here. You have the total volume of the cylinder. So the box in this case is the cylinder, the entire cylindrical nanotube to be 31420 nanometers cube. And then you have the volume of one atom, or the volume per atom, which is this that we found. And we found it to be this 0.017078 nanometers cube. So 0.017078 nanometers cube per atom, because it's still the volume of atoms. So we can say per atom, right? So we do this calculation: 31420 over 0.017078, and we have here 183. Am I getting it right? Okay, 1, 2, 3, 4, 5, 6. Okay, so 1,839,793.887 atoms. Okay, so the number of atoms in the entire volume is 1,839,793.887 atoms. So we've done number 7. Now it says number 8. Divide the total number of atoms on the surface by the number of atoms in the entire volume of the cylinder or nanotube to obtain the fraction of atoms on the surface. Let me just show it again. Divide the total number of atoms on the surface by the number of atoms on the entire volume of the cylinder or nanotube to obtain the fraction of atoms on the surface. Okay, so the total number of atoms on the surface, we found that to be the number of atoms on the surface, yes, to be this. And we are saying we will have to divide it by the number of atoms on the entire volume, which is this, to find the fraction of atoms on the surface. Okay, so you have this pen. We have found the number of atoms on this curved surface, on the top surface, on the bottom surface. And we are going to divide it by the number of atoms both on the surface here, top down, and inside. So that's the number of atoms of the entire volume. And that will give us the fraction of atoms on the surface. Okay, or let's say you have 5 pens somewhere. Like I have 5 pens in my bag and I pick out one. The fraction of atoms the fraction of pens I have picked out is the 1 over the total number of pens that were in my bag that I picked one out. So 1 over 5. That's the fraction of atoms that I have picked out. Okay, so we have 122,998.0786 atoms all over 1,839,793.887 atoms. And then we do the calculation: 122,998.0786 over 1,839,793.887. And we obtain 0.0669 approximately. Okay, so therefore the fraction of atoms on the surface, okay, the fraction of atoms on the surface is 0.0669. So this is all that we wanted to do, okay, and this is what we've gotten. So the fraction of atoms on the surface is 0.669. So the whole point we are trying to make is that for nanotubes, okay, when the diameter is small, the fraction of that on the atoms, the fraction of atoms on the surface is big. And when the diameter is big, the fraction of atoms on the surface is small. So an exercise is repeat the same procedure or calculations for the same 100 nanometers long nanotube, and then in this case the diameter is 5 nanometers instead of the initial one which was 20 nanometers. Use 5 nanometers, and then the other constants remain the same. Density is 10.4